Welcome to this video on mathematics, focusing on sequences and arithmetic progression. This is part of our Week 3 study on advanced series analysis. In this video, we will define sequences, understand the structure of arithmetic progressions, calculate common differences, find the nth term, compute sums, and apply these concepts to real-world problems. Mathematics is the science of patterns. Sequences are lists of numbers or objects that follow a specific, predictable rule. They are crucial for scientists, financial analysts, and engineers to make predictions and design stable structures. Let's begin with Section 1, the meaning of sequences. A sequence is an enumerated list of objects or numbers where order matters and repetitions are allowed. Terms are typically denoted by letters with subscripts, such as A1, A2, and so on. Here, we see how terms correspond to their positions. The variable n always represents a natural number, as it identifies the specific position of a term within the sequence. Sequences can be finite or infinite. A finite sequence ends after a specific number of terms, while an infinite sequence continues indefinitely, often indicated by an ellipsis. Most sequences follow a specific rule for change. These include additive rules, multiplicative rules, or algebraic patterns like the square rule. For example, if the rule is 3n plus 1, we can easily find terms by substituting the position n. For the first term, we get 4, for the second, 7, and for the 10th, 31. Moving to Section 2, we explore different types of sequences. Arithmetic and geometric sequences differ in how they change. Arithmetic sequences use addition or subtraction, while geometric sequences involve multiplication or division, leading to exponential growth. The Fibonacci sequence is unique. Each term is the sum of the two preceding terms, starting with 0, 1, 1, 2, 3, and so on. A sequence is considered harmonic if the reciprocals of its terms form an arithmetic progression. For example, the reciprocals of 1/2, 1/4, and 1/6 form an AP with a common difference of 2. Can you identify these types? Sequence A is arithmetic, B is geometric, and C follows the Fibonacci pattern. Finally, we move to Section 3. A deeper look at arithmetic progression. An arithmetic progression is a sequence where the difference between any two consecutive terms remains constant. This constant value is known as the common difference, represented by the letter D. The common difference determines the behavior of the sequence. If D is positive, the sequence increases. If D is negative, it decreases. If D is 0, the sequence remains constant. To calculate the common difference, simply subtract any term from the term that follows it. The formula is D equals A-n minus A-1. Visually, we can categorize AP behavior. Sequences with a positive common difference are increasing, those with a negative difference are decreasing, and those with a 0 difference are constant. Let's practice identifying D. For the first sequence, the difference is 8. The second gives -3, and the third reveals a difference of 0.5. Now let's move to Section 4, determining the formula for the nth term. By examining the pattern of an arithmetic progression, we can derive a general formula that allows us to calculate any specific term within the sequence. The general formula is A-n equals A plus n minus 1 multiplied by D. This is a powerful tool to find any term without listing the entire sequence. In this formula, A-n is the value of the term at position n, A is the first term, n is the position or rank, and D is the common difference. For the sequence 5, 8, 11, 14, to find the 100th term, we use the formula with our values. A is 5, D is 3, and n is 100. This gives us 302. If we want to know which position corresponds to a specific value, like 121 in the sequence 1, 6, 11, we set up the equation and solve for n, finding it as the 25th term. Here is a quick challenge. Find the 15th term of the sequence 100, 93, 86. Using our formula, we find the answer is 2. Finally, we reach Section 5, understanding the sum of the first n terms. The young mathematician Carl Friedrich Gauss famously discovered how to quickly sum integers by pairing terms from opposite ends of a sequence, revolutionizing how we calculate series. To wrap up, remember the distinction. A sequence is simply a list of numbers, whereas a series is the result of summing those terms together. The general sum formula is used when you know the first term and the common difference. It allows for the calculation of the total sum of any arithmetic sequence. Alternatively, you can use the sum formula involving the last term when both the first term a and the final term l are already known. For the sequence 3, 7, 11, finding the sum of the first 20 terms involves identifying a as 3, d as 4, and n as 20. Applying the formula, we reach a sum of 820. Now let's explore section 6, applications in problem solving. In a theater seating scenario, if the first row has 20 seats and each subsequent row increases by 2, we can calculate the total capacity for 15 rows by applying our sum formula, resulting in 510 seats. Financial growth can also be modeled this way. If J saves $100 in the first month and increases savings by $50 monthly, after 12 months, the total saved is $4,500. Let's recap the core formulas. Use the general term formula for finding specific values, and the two sum formulas for calculating totals, depending on whether you have the common difference or the last term. Here is a final challenge. Try finding the 40th term of the sequence starting with 10, calculating the sum of the first 50 positive even integers, or determining the total logs in a 10-row pyramid. Thank you for joining this masterclass on sequences. We hope these concepts help you master arithmetic progressions. If you have any questions, feel free to review the material. This video utilized various images to illustrate mathematical concepts. Credits are provided here for the source material used throughout the presentation.